In this lesson, we're going to talk about complex fractions, which is basically, as the slide says, a fraction over a fraction. Now, when we look at a setup of complex fractions as such, there's a couple ways to do this, and I'm going to show you both. And you can do whatever you're most comfortable with, but I would probably recommend the second way, but I'm going to show you the first anyways because some people feel more comfortable doing this. All right? The general idea is we've got to take and simplify the subtraction, simplify this addition, and then divide the two. Okay, now, if I want to add or subtract these two fractions, I need a common denominator. So that common denominator on the top is going to be 8. I'd have to multiply these guys by 2. And 12 in the denominator, so I'd have to multiply the top and bottom here by 12. All right. I get 6 over 8 in the first term, minus 1/8 in the second term, over 24 over 12 in the first term, and 1 over 12 in the second term. Simplifying these, we know when we add two fractions, we take and leave the denominator to the same. Add or subtract the numerator, I have 5/8 and 25/12. Now, what we really have is we have, again, another complex fraction, a fraction over a fraction. But in, what, 5th grade maybe, we wrote divisions something like this, where we had 5/8 divided by 25 over 12. And we know that's the same as multiplying by the reciprocal. So the reciprocal of 25 over 12 is 12 over 25. These guys are going to reduce all over the place. I get a 1 here, 5 here, 3 here, and a 2 here. So I multiply my numerators, get 3, multiply my denominators, get 10, problem done. Now, the second problem works much the same, except in this case, rather than taking and finding a common denominator of just the numerator and denominator, I'm going to find the common denominator of all terms in the numerator and all terms in the denominator. And the thing to point out here is that the denominator of the two is actually a 1. So I need a common denominator of 4, 8, 12, and 1. And that lowest common denominator is going to be 24. So like in the other problem, I need to multiply by a form of 1, but I'm going to do it this time to the entire numerator and the entire denominator. So notice the difference. In this problem up top, I worked just with the numerator, just with the denominator. Now I'm working with the entire numerator and the entire denominator. So I'm going to distribute that 24 to each term and watch what happens. The 24 and the 4 reduce to a 6, so that's 6 times 3. The 24 and the 8 reduce to a 3, so that's, 3 times 1. And this guy is not a subtraction or an addition, but it's a subtraction. So put my subtraction right here. Now, next. In the denominator, I'm going to have a 48 because 24 times 2 is 48. The 12 and the 24 are going to reduce to a 2, giving me a 2 times a 1. Notice what I have left. Effectively, I've gotten rid of all my denominators in the numerator and all my denominators in the denominator. So thus, I have a fraction left, that fraction being 18 minus 3 over 48 plus 2. This leaves me with 15 over 50, which, what do you know, reduces to 3/10. I'm going to leave it up to you as to which way you want to do these problems. I think for the simple fractions, you're going to see that these are pretty easy on the top. But when we get tougher, like in the next example, you may want to go to my way. So now we're looking at a situation where we have variable terms in the numerator and denominator. All right, I have to find a common denominator of c squared, c, and c squared. Once again, we have a situation where in this numerator, we have a denominator of 1 under the 9. So my common denominator, we know this from algebra 2, is c squared over c squared. I'm going to multiply that to all terms in my numerator and all terms in my denominator. All right, multiplying through, I get 9c squared. The c squared and the c squared reduce in the second term, so I'm left with 1. C and c squared reduce to a c, so I'm left with 3c. And the c squared and the c squared reduce to 1, so I'm left with 1. And I notice in this term, my numerator actually factors. That's the difference of squares into 3c minus 1 times the quantity of 3c plus 1, all over 3c minus 1. And we know that anything that's the same reduces. So my answer, simplified, is just 3c plus 1. In this example, you're going to notice that we have two completely different terms, 3x plus 1 and 1 minus 3x in my denominators. Now, again, under the 2, we have a common denominator of 1, or a denominator of 1, sorry, and under the 3, we have a denominator of 1 as well. All right. Our common denominator is going to be actually the product of both denominators since they are completely different. Let's use a different color here. All right. I'm going to take and multiply by that common denominator of 3x plus 1 and 1 minus 3x to both the numerator and denominator. What this does is it allows me to multiply by 1. Therefore, I'm not changing the value of my complex fraction. And I'm going to take and distribute this term to both terms in my numerator and in my denominator. This is going to get a little bit ugly if you watch. The 3x plus 1 will reduce, leaving me with 3x plus 5 in the first term, and this new multiple of 1 minus 3x. Now you'll notice in the second term, nothing reduces. So I have 2 times the multiplication of the common denominator, 3x plus 1, and 1 minus 3x. In my denominator, we have a similar situation where in the first term, nothing reduces. So I have 3 times 3x plus 1 and 1 minus 3x. But in the second term, you'll notice 1 minus 3x reduces. So I'm left with a multiplication of 3x and 3x plus 1. Here's where the difficulty lies. Now, you'll notice in the numerator, I have a couple of terms in common. Those terms are this 1 minus 3x and this 1 minus 3x. Since those terms are in common, I'm allowed to factor those out. It's kind of like factoring out a GCF. So I'm going to pull out a 1 minus 3x. And what I have left is a multiplication. Oops, got my disappearing pen on. What I have left is a multiplication of 3x plus 5 times, after I pull out a 1 minus 3x in the second term, I have a 2 and a 3x plus 1 left. In my denominator, I notice I have a 3x plus 1 in common. So I'm going to pull that out like a GCF. And again, very similar to the last problem, when I pull out a 3x plus 1 from the first term, I'm left with a 3 and a 1 minus 3x. In the second term, after I pull out a 3x plus 1, I'm just left with 3x. Now you'll notice I can combine what's inside each of these brackets. So I have in my numerator 1 minus 3x. Inside the brackets, I have 3x minus 6x, which is negative 3x. And I have 5 minus 2, which is 3. It's positive. In the bottom term, 3x plus 1 will be multiplied by the combination of what's inside the bracket. So I have the number 3, and there's a negative 9x plus 3x, which is a negative 6x. In algebra 2, all over the place again, we've got terms that are going to take and factor. So as I factor that, we notice in the numerator, I have 1 minus 3x. I can pull out, let's pull out negative 3. And I have x minus 1. And in the denominator, I have 3x plus 1. And I'm going to pull out, let's go a negative 3 again. And when I do that, I'm going to take, and I'm going to write my x term first, I think. So that's going to give me a positive 2x and a negative 1. Now, if anything reduces, I'm done. And I notice that these 3's both reduce. So my final answer is 1 minus 3x times x minus 1 over 3x plus 1 multiplied by 2x minus 1. Again, a little bit tougher. Moving forward. Now we're going to jump into the pre-calculus stuff. That was a review of Algebra 2 that we're going to need down the road. So let's start with some definitions. First definition we're going to talk about is a relation. Okay, and as you can see, a relation is just a set of ordered pairs. What am I talking about, ordered pairs? I'm talking about x and y coordinates, so some x and y. Domain, these are the defined x values for the function. Now you're going to see in a couple of minutes that there are x values that are undefined for certain functions, and I'll show you as we move along. The range is the defined y values for a function, and we're talking about functions. So let's define it. A function is a relation or a set of ordered pairs such that for every x, there exists a unique y, okay, which means exactly one y. Let's move on. So here I have some relations for you. All right, and these relations are sets of ordered pairs, and I want to know what the domain and the range is for each of these, and then I want you to tell me if each of these are a function. So the domain, in this case, is the set of all x's. Well, that's just 4, 8, and negative 5. That's my domain. My range is the set of y values. So that's 3, 2, and 3. All right. Now, we need to know if this is a function. So for every x, there exists only one y. What I like to do is I like to think about graphing these things. And if I were to graph all these points, 4, 3 looks like to be something here, 8, 2, it's way over here and down, negative 5, 3 is somewhere here. So the definition of a function says that for every x, there is only one y. So if I look at each of these x values, negative 5, 4, and 3, is there only one y value associated with it? Yes. And another quick way to talk about this is you're looking for a vertical line test. And what a vertical line test says is it says if you can take and draw a vertical line any place in your function and it only goes through one point at a time, then it's a function. Great. So let's look at the second example. I've got 3, 4, 3, 5, and 3, 6. And I want to take and state the domain, which is just all the x values. All right. So I've got 3 sets of 3s. Now, you can write all 3 3s if you want, or just 1 3. A lot of people just write 1 3. And the range is going to be 4, 5, and 6. Now, we want to see if this is indeed a function. So I'm going to use this vertical line test idea. Here's 3, 4, somewhere here. 3, 5, and 3, 6. Now, if I draw a vertical line, you'll notice that vertical line is going to pass through all 3 of those points. So this is not a function. Let's move on. Now, I want to find the domain of this function. So I'm telling you it already passes a vertical line test. Now, in Algebra 2, we learned how to graph these, but right now I'm not going to hold you responsible for doing that. I just want you to be able to tell me all the x values that, in a sense, work for this function. So what x value can I pick that I can plug it in and get a y value out? Like I can pick 100. If I pick 100, 5 over 100 plus 4 is 5 over 104, not a problem. But there's one value for this fraction that will make the output undefined, all right? And it's all going to key on this denominator. We know in fractions that you can never divide by 0. So if that's true, all right, when I plug a -4 in for x, I get 5 over -4 plus 4, which gives me 5 over 0. That's undefined. Therefore, the domain, and this is how we're going to write it, all x's such that x is not equal to -4. And that's my domain. Moving to the next example. In this case, now we have a square root that we're looking at. And when we talk about square roots, there are some issues with square roots. We know that we cannot have a negative value inside a square root. So what that tells us is it tells us that anything under the square root, in this case 2x plus 7, has to be greater than or equal to 0. And this is how we're going to state the domain of this. When I solve this inequality, I get 2x is greater than or equal to -7. And x is greater than or equal to -7 over 2. This, x is greater than or equal to -7 over 2, is my domain. If I pick a number that is less than -7 over 2, -10, for instance, 2, let's do this, times -10 plus 7 gives me a negative value under the square root, all right, which is undefined. So my domain, once again, is going to be x is greater than -7 over 2. Now, in this function, it's also a square root, but it's a special case because within that square root, I have this right here, x squared, being a term that's always going to be positive. So whatever number I plug into this x is going to come out positive, and thus I'll be able to take the square root of it. This is a special case. You got to understand the situation. So in this case, I have all real numbers as my domain. So that's it for today. What I'd like you to do is I'd like you to take and answer each of these questions on the form provided for you below, and then we'll discuss them tomorrow. Thanks.